The overall goal of this work is to visually demonstrate the production techniques of biopolymer aerogels using amidated pectin as a model biopolymer and water, ethanol, and carbon dioxide as solvents.
Biopolymer aerogel production is a three-step process which utilizes water for the gel formation, ethanol to replace the water, and supercritical CO2 to remove the ethanol.
Carbon dioxide has a huge impact on this process as it is a quintessential component in aerogel production.
Our investigations of how carbon dioxide transforms biopolymeric solution into aerogel has led us to the understanding that CO2 can not only gel biopolymeric solution but also can help to produce aerogel in one step, one pot approach. And we are going to discuss it in this video.
This section demonstrates how amidated pectin and calcium carbonate dispersion is made in water. However, the procedure can be adapted to making many other solution mixtures. Homogenize a 2% pectin in water solution at high speed for 2 minutes to make a viscous solution. Then, check the pH. If it is lower than 6.5, titrate with 0.5 molar sodium hydroxide to neutralize the solution. Next, weigh out and mix in the calcium carbonate.
It is not necessary to adhere to this degree of cross-linking. However, too much cross-linker can lead to reprecipitation and negatively affect the surface area of aerogels.
Finally, homogenize the mixture at high speed again until a white homogeneous dispersion is obtained. Begin with transferring the prepared suspension into open polypropylene molds or glass petri dishes. Then, place the molds into a high-pressure autoclave. Pressurize the autoclave with carbon dioxide up to 5 megapascals at room temperature. The depth of the solution in the mold determines the gelation time. A thin 2 mm gel can be made in less than 30 minutes. After gelation, slowly depressurize the autoclave at 0.2 megapascals per minute. Any quicker and the gel can break. When fully depressurized, open the autoclave and remove the molds. Remove the hydrogels from the molds by turning them over and, if necessary, pry them out with a spatula. A perfect hydrogel looks homogeneous. For each gram of prepared hydrogel, make 10 grams of ethanol and water at a 1:9 weight ratio. Then, immerse the hydrogels in the ethanol and water mixture for 12 hours. The equilibration time is mainly dependent on the sample thickness. Later, immerse the gels in a 3:7 weight ratio solution of ethanol in water. Shrinkage of the gel will occur.
Shrinkage is strongly dependent on the concentration gradient during solvent exchange, the biopolymer type and concentration, the size of the gel, and the degree of cross-linking. Always try to minimize the shrinkage because too much shrinkage will lead to poor aerogel properties.
Ultimately, the final concentration of ethanol in the gel should be greater than 98% by weight. Measure it using the density meter, and once confirmed, proceed with supercritical carbon dioxide drying. Prepare the gel sample to be dried using supercritical carbon dioxide. Fill the autoclave with ethanol. Use between 2 and 10% of the autoclave's volume to prevent premature solvent evaporation. Complete immersion of the gels is not necessary. Now, heat the autoclave to 323 Kelvin and apply 12 megapascal of pressure using carbon dioxide. Periodically, replace the carbon dioxide inside the autoclave while keeping the pressure constant. Around 6 or 7 residence volumes are typically required. The drying time depends on the gel thickness. As before, slowly depressurize the autoclave. Then, store the prepared aerogels in a sealed container or a desiccator. These aerogels are sensitive to moisture in the atmosphere. An alternative to depressurizing is to start the solvent exchange in the pressurized autoclave. To accomplish this, pump the ethanol water mixtures into the autoclave stepwise, ensuring the gel remains submerged in the liquid. This takes about 90 minutes for a 2 mm gel. Once the desired solvent concentration is reached, commence with supercritical drying by increasing the pressure from 5 to 12 megapascal using supercritical carbon dioxide. For a 2 mm gel, the process of gelation, solvent exchange, and drying should only take about 3 hours. Biopolymer concentration plays an important role in the transparency of the hydrogels. 1 and 2% samples were not transparent, but 0.5 and 1/4% samples were. These percentages were given by weight. Bubbles were created in the hydrogels during the depressurization when the dissolved carbon dioxide left the gel water system due to a decreased carbon dioxide solubility. A deep reduction in the biopolymer concentration to 0.25% yielded stable but fragile hydrogels. The obtained aerogels were ultra-porous and had low densities. Their surface areas were measured by nitrogen adsorption. In the 4 to 150 nanometer pore size range, their volumes were measured by the Kelvin model of pore filling with nitrogen.
After watching this video, you should have an understanding of how to dry gels in organic solvent with supercritical carbon dioxide, and also how to dry hydrogels using organic solvent and supercritical carbon dioxide.
Also, you should understand how to transform biopolymeric solutions into aerogel in one pot process.
Once mastered, this whole procedure from biopolymer solution to aerogel can be done in as little as 3 hours, depending on the gel thickness.
While attempting this procedure, it is important to monitor the pH value of the initial solution, the depressurization rate after the gelation, the final solvent concentration prior to supercritical drying, and the depressurization rate after supercritical drying.
We do believe that this technique will attract many researchers and engineers alike and force them to produce various materials and products in the field of thermal insulation, pharmaceuticals, nutraceuticals, and so forth.
Don't forget that ethanol is a flammable solvent and it is used in a high-pressure environment for this procedure. Using personal safety precautions and safe laboratory and equipment operating procedures is essential for this procedure.